Today we have Aaradhya Pandey talk about his recent work on privacy and the S square equal to K conjecture.
Thanks much, and yeah, thanks for inviting me. So although the title says information, computation, and quantization, the real title talk should be this infinitely divisible privacy. And but I'll try to hint a little bit on what do I mean by this overarching theme, which is information, computation, and quantization. Okay, so let's see. And okay. So like at the outset, this is what I want you to have in mind. So I'll describe the result, let's say in the first five slides, without much of motivation, and then the rest of the slides, rest of the time, I'll try to motivate. So the thought process is, I guess I'm assuming that you're all familiar with the let's say the problem of hypothesis testing, and even the simplest kind. So what is the problem of hypothesis testing? So you have a real number. Let's assume you have a real number, and then you believe that the real number is generated either from a distribution P0 or P1. For example, normal distribution with mean 0 variance 1, or a normal distribution with a shifted mean like theta comma 1. Mean is theta, variance is 1. So that's like a pair of probability distributions, and you're trying to understand that whether your sample is coming from which one. You don't know that, so you're trying to determine that. So here we'll have a little bit twist, which is the following, that instead of one hypothesis testing problem, we'll have two. Okay. So this is the twist. So I mean, it's not a twist, but the idea is we'll have two hypothesis testing problem. Think of like normal distribution. So this is the example you can keep in mind, that I am trying to understand my hypothesis testing problem. I'm trying to decide my hypothesis testing problem. That basically means I'm trying to understand that my same sample, whether it came from P0 or from P1, you have your own hypothesis testing problem, and you are trying to determine whether it came from R0 or R1. So that's, I guess this idea is hopefully clear to people. Now, if just for the sake, I guess I'll ask, like which one of the problem do you think is easier? Which one of the hypothesis testing problem is easier? The P0 version, P0 P1 version, or R0 R1 version? I mean, I don't see many people, but okay.
R0, R1
Oh,
looks
Yeah, okay.
easier
So
to me.
that's the easier. So we have this intuition that the farther the mean goes away, easier should it become. Yes. Okay. Now so this is like the okay. So this is the problem, and then the mathematical minds, I guess, I guess you have this one world or something like that. The title of the seminar. So okay. So now the question is, how do we really mathematically see this explicitly? So is it the thing that we would like to write that mu2 is greater than equal to mu1 and the problem is solved? But in general, how will it be? Okay. So this is the problem. Now I'll on one sentence, I'll say that how will this appear? So in differential privacy, at some point or end in time, we'll see that the following, that we'll have some sort of a sample, and we'll like to trying to understand whether the sample came from two distributions. Now we'll not really have something absolute measure to compare with. We'll really have another hypothesis testing problem, and this is the baseline we'll consider. Okay, that might be vague, but let's continue. So let's okay. So now what is the question at this level, that I have a hypothesis testing problem, you have a hypothesis testing problem, and there's an equivalent question, which is I want to understand which one is easier. Okay, and this we can say this statement in 10 different ways, but the intuition is what we mean, that which one is easier. Now the question is, how do I mathematically write this down? And this is where the solution comes, and the solution is what is called Blackwell ordering to some. So in 1950s, David Blackwell, or maybe people, maybe earlier too, I don't know, like, so this is the name, let's say, is usually given in the statistics literature, and this is called Blackwell ordering. And in information theory, there's also another name, which is channel comparison. And in probability theory, we have this is also sometimes called stochastic domination of appropriate order. Okay. So I guess this intuition that we have two hypothesis testing problem, and we're trying to compare. Now, how do I mathematically write this down? And the tool that one uses is some sort of a partial ordering, and that partial ordering has like multiple different names in different communities. Okay. So okay, so I've just written down the same question. You can keep the normal distributions example in mind. Okay. So here is the key object throughout the talk. Okay, so maybe I'll go through this very slowly. So what do I have? Think of P0 is P. Think of P1 as Q. And you can like the same analogously think about R0 as P, R1 as Q. So the whole idea is given to distributions P and Q, I construct something. Okay. Now, maybe on the face of it, you might think that how do I compare that my distributions are, so to speak, closer than yours or further than yours? Is we might have a thought that why don't we compute total variation distance between P0 and P1? And maybe in your case, you also compute total variation distance between P0 and R0 and R1. And whichever one is smaller, we'll declare that they are nearby and harder to distinguish. Maybe somebody does not like that much total variation distance, some other notion of divergence, something like KL divergence or something. Maybe we can try doing that too. Compare the two real numbers. Okay. Here is the twist that we'll not really compare two real numbers. What we'll compare is the following, that given two probability distributions, we'll generate a curve. And I'll show you pictures right in the next slide. What is this curve? So the curve is the following, which is we have two distributions and we assume that we have a sample. Think of the normal 0 and normal 1,1 example. Okay. And in hypothesis testing, you're supposed to construct a test. And what is a test? A test is a measurable functions from your domain to a real number, which is between 0 and 1. So the ideal thing to do is to output 0 or 1. 0 corresponds to P0, 1 corresponds to P1, something like that. And then, and P0 and P1 are distributions here, or P and Q. And then you will make two kinds of errors. So in statistics, it is usually called type 1 error and type 2 error. So you fix the type 1 error at this level. And what is type 1 error? The type 1 error is the following, which is you believe the reality is P, but your test procedure outputs 1. And this is type 1 error. And type 2 error is the other thing, which is you believe the reality is Q, you believe reality is P, but you're outputting Q. So that's the idea. So you have two realities, and the reality is 0, you're outputting 1, reality is 1, you're outputting 0. I hope this idea is clear, this type 2 error and type 2 error. This is like one way of understanding things. Okay. Now, so the key thing to keep in mind is the following, that what we are computing is not a real number, we are computing a function. Given two distributions, we are computing a function, and that is kind of utmost importance. We are not computing a real number like total variation distance or KL divergence. Okay, sorry, what happened? Okay. Then, okay, now what I will do is focus on step 3 first for now, and then we'll go back to step 2. So just like we did, or we had in mind in our situation, that maybe we compute total variation distance and compare. Here, what I will do and what you will do is I will compare my own curve. You will come up with your own curve and we'll compare. And it will also turn out that in the Gaussian case, as we expected is what will happen. So what we expect is what we see. Okay. So this is the mathematical way of saying that my hypothesis testing problem is easier than yours or harder than yours. I mean, depending on what this sign is. So the higher you go, the harder it is. The higher you go, the harder it is. And that is basically connected to this inf. Okay. So this is a step 1 to step 3. But before going to step 1 to step 3, I need to also ensure another thing. And this is kind of important. So when we are trying to compare two things, let's say an element little a with little b. And what is little a here? A little a here is an entire function, and little b is also an entire function. So the first thing that we try to do is, why don't we look at the set of all such functions? Okay, so this is the set where we look at all such functions and where we vary all these pairs of probability measures and all these sets. And this is the class of functions on which we'll define this ordering, that we take two elements here and we define two elements like f and g from this set. And we say f is greater than equal to g if f is pointwise greater than equal to g. And now in statistics or in general, there is a theorem, classical theorem from 1950s or maybe somewhat later days. What does it say? It says the following, that this class of functions on which you're trying to define this ordering or comparison has an explicit description. So this set is nothing but this set of functions. It has 4 properties. So what does it mean? It means given P and Q, if you compute this TPQ, you will get a function which satisfies all 4 properties, and vice versa. That means if you are given a function on this from here to here, and if you satisfy these 4 properties, then actually you can construct a P and a Q. Okay. So this might look a little bit esoteric or from a little bit from far from what we had in mind. But just to go back, the idea is I have a hypothesis testing problem, I construct a curve. You have a hypothesis testing problem, you construct a curve, and we define it like this. So this is our notion that we'll check this whether this happens or not. And then just so that we have a set in the background. So this is the set of all such functions. And this characterization, so to speak, helps us see what those functions look like. Okay. So this is from all in the past, let's say. So this is how it usually looks like. So typically this TPQ looks like this kind of curve. So it remains always below this curve 1 minus x, the anti-diagonal, or appropriately said, or the diagonal, whatever you want to call it. So it remains below 1 minus x. And it is convex, continuous, and non-increasing. Okay. And just like if you have 2 such curves, you can compare f and g, and you can also see that not all pairs are comparable. So this is the partial order. That basically means if you take 2 elements, f and g, from that set tau, not all the time you'll have that f is greater than or equal to g at all points. So this kind of drop, sometimes up, sometimes below, might also happen. Okay. So maybe I'll pause for 1 minute. Okay. So is this clear? Hopefully now. So what I've described is this notion of hypothesis testing problem, pairs of hypothesis testing problems. And in order to define a comparison, I construct a curve, you construct a curve, and we compare. Okay. And there is a background. Background is this set of all such curves. And this is this tau. Okay. So this is the abstraction. Now focus on this set. So this is some sort of, you can think of it as, let's say, a vector space. I mean, it is not a vector space, but think of it as, in your mind, if you want to think of it that, it's a vector space. It is not, but let's just continue. Okay. Now, just like on a vector space or on a group, you define an operation. Okay. Just like addition of 2 vectors is an operation on a vector space. On this set, this tau, the set of all such hypothesis testing problems, we define an operation. Okay. Now, all this is abstract as of yet, and this is like the later part of the talk to make sense. Now, the idea is the following, which is I take 2 curves, and so I take this curve TP1, Q1, and I take another curve TP2, Q2, and then I define the third curve is this. Okay, and this is literally the hypothesis testing problem, which is one sample has 2 pairs of real numbers. And the first pair is coming from, you don't know whether it's coming from P1 or Q1. The second pair, you don't know whether it's coming from P2 or Q2. But you also know that the first real number is independently generated from the second one. So that's the hypothesis testing problem that this one captures. Okay. So this is the operation. So in a vector space or in a group, you define an operation, just like addition. This is the operation, let's say, on our set tau. And then the key result is the following, which is something about a convergence of, so to speak, convergence of objects under this operation. So you can think of in a vector space, you have a sequence of vectors, and you get the sequence of vectors by some version of addition of vectors. And you ask what happens in the limit in that vector space sense. So we'll also try to do the same. And then, okay, so this is the result in abstraction without much context. Okay, so what does the result say? So ignore for this moment this extra small condition here. So this condition corresponds to the following fact, that this condition, I'll just say one sentence, that this condition is the same as that Qn is absolutely continuous with respect to Pn. Okay, now forget about that condition. We take a sequence of curves. So think of you have this image in mind, which is this box, the unit box. And you have this kind of curves, and you take a sequence of them, F1, F2, F3, and so on. And then you tensorize. Okay. So this is like, okay. So this is like on the vector space side, you take a random variable and then take independent copies and then take sum them. So that's the high level idea. And then you ask that you assume that it converges. Okay. So you take a function, you take its nth product. So something like in a triangular array, you take a random variable, you take n independent copies of that random variable, and you sum them, and you assume that that random variable situation converges in distribution to a limiting object. And in this context, you assume that it converges to a limiting function of the same kind. Okay. And then you ask the question that what can this be? So if you converge under this operation, what can you be? Okay. So you start with a set tau. However you want to visualize this set tau, what did you do? You consider a triangular array, and at nth stage, you consider this function fn, and you do this operation n times, you get this fn tensor to the n. Okay, and you assume that this converges to a limiting object. And what is this limiting object? You believe that the limiting object is of its own kind, like this. And then you ask the question, what will this object be? And the key result of this says is that this object will precisely be this subclass. And the way to think about it, I mean, not the random variable example I gave, but also in the random variable example, you also know that the limiting objects look like infinitely divisible distributions. But even in the simpler situation, maybe unit sphere has like a specific structure as a subset of a specialized subset of the vector space, if it has a norm. Here, what we get is as convergence to a limit, we not all the time will get all possible curves. We'll get a specialized subclass of curves. And this is what I'm calling infinitely divisible privacy. Okay. So what is this curve? So convergence will allow us not to converge to any arbitrary trade-off function or element of tau, but it will converge to a specialized subset of tau. And what is the specialized subset? So the specialized subset will be TPQ. Now, P won't be an arbitrary probability measure, Q won't be an arbitrary probability measure as it was in tau situation, but it will be a specialized case. P will be an infinitely divisible distribution, and Q will be a probability distribution on R, and that is exponential moment of P. So basically, P has two restrictions. It has to be an infinitely divisible distribution, and the second restriction is exponential moment of P has to be equal to 1, and Q is actually equal to that distribution. Okay. So this is the result in abstraction. Now I will explain how this operation makes sense. Why do we need to consider this? And why do you need to consider a triangular array? And how does it connect to the previous framework, which is Gaussian differential privacy? Okay. So yes. And for those, I'll briefly touch upon that. What does it mean to say a probability distribution being infinitely divisible? It is known that in order to understand the distribution, it's enough to understand its characteristic function or Fourier transform. And infinitely divisible distribution is by definition, or one equivalent definition says that its Fourier transform or log Fourier transform has an explicit form. And as you might recognize, that infinitely divisible distribution has two components. One is the Gaussian component, and this is literally the characteristic function or log characteristic function of Gaussian. And this comes from the Gaussian part, and this comes from the Poisson part. Okay. So that's it. So this is really the abstract result. And then S square equal to 2k thing that appeared somewhere will also be a consequence. Okay. So now we forget all this abstract situation. Now we come to, let's say if you ignored the first part, now let's start refresh. So okay, what am I going to talk about? I'm going to talk about differential privacy and a specialized definition. So you can forget the rest for now. The hypothesis testing problem, pairs of hypothesis testing problem, and trying to construct not a real number but a curve. I come up with a curve, you come up with a curve, and then I and you compare. But suddenly, instead of comparison, we had a sequence of curves, and we in fact took tensor products. Okay. So these are essentially some of the motivating questions. So what is differential privacy? I'm going to explain now. And then I'm going to explain what is Gaussian differential privacy. So these were from that paper called with the title Gaussian differential privacy in a previous paper. And then this recent preprint is what is this infinitely divisible privacy and what is Poisson differential privacy. So, okay. So on a high level, you can think about the following, which is I told you that this P had an infinitely divisible part. And in a previous paper, this was discovered. The Gaussian part was discovered. And now the bigger thing is discovery is basically this, that this has not just Gaussian, but also Poisson. So Gaussian differential privacy becomes Poisson differential privacy, infinitely divisible privacy. And then what I say is, why don't we remove the Gaussian part, and then it will purely become Poisson differential privacy. So that's the chain of thought. The most general version, then Gaussian, then infinitely divisible, then Poisson. And then if I have time, I'll briefly talk about this information computation and quantization. What does it mean? Okay. So I don't know how much time should I spend on differential privacy, but the thought process is the following. So differential privacy is about, what is it about? So, okay, so somebody has data x1 through xn, and one is supposed to, let's say someone asks, let's say I'm a hospital, I have the data x1 through xn, and somebody asks from the public, why don't you release average height? So that basically means I have to release 1 over n summation xi, if xi were the heights of people. But if I literally release 1 over n summation xi, then there is this problem that upon seeing that output, some adversary might be able to understand whether certain data point, or rather certain individual was part of the data set or not. So that's the idea. Maybe with heights, it's okay if your neighbor learns that you were part of the data set. But maybe if it was not about height, but some sensitive information, maybe you do not want your neighbor to know whether you are part of the data set or not. So this is this idea called when you release some public health dashboard. And then also, yeah, so okay. So 1 over n summation xi is some sort of accuracy as from the statistical understanding that this is some sort of accurate if you assume x1 through xn are some notion of distributional assumptions, but that's not satisfied differential privacy constraint. Okay. So yeah, and this is precisely what I said, that upon looking at the output, which is 1 over n summation xi, or the average height, an adversary should not be able to figure out whether a certain individual was part of the data set or not. So that's the high level idea. And that's where the notion of a single hypothesis testing problem comes. So you at least start to see hypothesis testing problems. And what is the promise of differential privacy, differentially private hypothesis testing, or sorry, differentially private machine learning or statistics? The promise is the following, which is, okay, so if I change one person's record, so that means 1 over x1 through xn, you remove one person, xn, and replace it with some xn prime, the distribution of the released output should only change slightly. Now remember, if you release 1 over n summation xi, and on the other side you release 1 over n summation xi, but replace xn with xn prime, actually distributions are very different. I mean, if you assume x1 through xn are fixed, then actually one is a delta at some different point, one is a delta at a completely different point. So you okay. So that basically says that one is to add external noise. That means even if x1 through xn are random, not a problem, but along with it, you have to add some amount of noise. Okay. So that's what is called usually the usual notion of privacy. Then there's also the graph notion of privacy, which is called graph differential privacy. What is the intuition behind this? And this basically says that person's record changes via a graph. So for example, let's say you are a company, I don't know, some company who holds a network, and then the thought process, let's say you're Facebook and you hold the Facebook network, and some public asks you to release a number of 3 cycles. So you have to release number of 3 cycles, but let's say as Facebook. And then the problem is, maybe I had a friendship with you, and so that's like an edge in the graph. But once Facebook released that number of 3 cycles, I don't want my neighbor to know whether I had a friendship with you on Facebook. So I don't want my neighbor to know upon seeing the output, the number of 3 cycles. So that's the idea, that if so Facebook should output number of 3 cycles in such a way, number of 3 cycles of the Facebook graph, so that if I change or remove one edge of the graph, the distribution does not change much. So it's about the distribution, not the real value. Okay. So now comes the notion of F differential privacy or a differential privacy. So okay, so what does it say? It says the following. So okay. Now, as I mentioned that one has to use external randomness. That means even if one sees x1 through xn, one cannot literally release 1 over n summation xi. One has to add noise, and adding noise is nothing but applying a Markov kernel as, let's say, from probability side, and a randomized algorithm from the CS side. And this stability requirement that was talked about earlier, that the distribution of the output should not change once you change something, is usually something like a Lifshitz requirement. But Lifshitz requirement on a Markov kernel. Okay, so this is the high level idea. And now I'll skim through fast, because I believe, I guess some of you have seen. So what is the definition of a Markov kernel? So the definition of a Markov kernel is basically I have a point on the left and I generate a distribution. And what are some examples to keep in mind? So the examples to keep in mind is this one. You can ignore the rest of the notation, but the key thing to keep in mind is in the case of a random walk, if you start from omega 1, you generate a distribution, and whether it is to the right or to the left, you go with your probability p to the right or with probability 1 minus p to your left. Okay. Now, so you can generalize this Markov kernel. So how do you generalize? Instead of just going to your left and right, you can go as far as you want. You can go as on the left as well. So that's the general transition matrix as we are familiar with, I'm hoping. And then, okay. So this is Markov kernel, but in the CS literature, once you implement it, that means how do you implement a random walk? You'll have to almost surely implement it, and that's usually what is called the randomized algorithm aspect, because they don't really care about the distribution. Sometimes you also need to implement it on a computer. Okay. And maybe more so to speak from the continuous side. So these are some sort of discrete examples, very let's say good enough for implementation purposes. But these are some sort of mathematically nice, continuous, and so on. So what is the idea? So this is also a randomized algorithm, but from the continuous world, but it's also the same as a Markov kernel. What does it do? So it stays at theta, and so m theta generates a distribution where you literally add the noise. Okay. And this is the Gaussian. And in general, in a group, you can add any arbitrary noise, not a problem. Okay. And in CS, it's also important that sometimes you do not add any noise. You literally output a function. So omega output f of omega. So that's the implementation. And when you write in terms of distributional notation, basically m omega is Dirac at f omega. Okay. So why am I doing all of this? We are supposedly discussing differential privacy. What happened to that? So differential privacy is what? It is on a high level, a Lifshitz requirement on a Markov kernel. So so in this slide, I'm just giving you multiple examples of a Markov kernel so that you feel familiar that Markov kernels are objects like this. Okay. And then, okay. Now, Markov kernels or randomized algorithm have many equivalent names. It is also called a statistical model, channel, and so on. And so this will be important, but I'll be brief here. So the idea is the following, which is okay. So Markov kernels, as we are familiar, that it takes probability distribution to probability distributions, and it takes functions to functions. Okay. What does it mean? It basically means that if you have a Markov chain and your initial distribution is P1, you apply if you hit with a Markov chain, then your the distribution at time 1 or 2, depending on where you initialize, the next step of the Markov chain will have marginal distribution M of P1. And the other side is the average. Okay, when you start at omega 1 and you are trying to understand expectation of F2 under this Markov chain M. Okay. So even if you forget for these two operations for now, how Markov kernels act on probability measures and functions, the key thing to keep in mind is differential privacy is a requirement on M, a Markov kernel. Okay. Now, slowly we'll see that so far we have seen the definition of a Markov kernel and some examples. Here, I think it's kind of important to keep in mind that we'll not really have just one Markov kernel, we'll have more than one Markov kernel. That's kind of important. And that's where you remember we took tensor products some in the beginning. So it will appear. So that's where the thought process is that let's say from the outside world, somebody asks you to release average height today. So that's like so you have x1 through xn, you output m1 of x1 through xn. Next day, somebody asks you to release average weight of the same population. So you release m2 of x1 through xn. On the graph example, if you are Facebook, somebody asks you to release 3 cycles today. Tomorrow, maybe 4 cycles. The next day, maybe 5 cycles, and so on. So you will not literally have one Markov kernel, but you'll have you'll have a collection of Markov kernels or more than one. Now, once you have more than one Markov kernels, you have to do algebra. Now, what kind of algebras are allowed within Markov kernels? So usually you can take convex combination, and that's the idea is you have multiple choices m1 through mk. With lambda 1, you choose to apply m1 on the point. With lambda 2, you apply lambda with probability lambda 2, you choose to implement m2 and so on. Okay. So this will not see much today, but I just wanted to give you this example. The other example is applying this random walk more than one step. So this is the multi-step random walk. The key thing that will appear today is the product. So what is it? So the idea is the following, that you release the statistic under M1, and then you release the statistics under M2, but you do so independently. Okay. And this is also the same as we are told in statistics, which is we have a model which is p theta, collection of p theta indexed over theta, and but we have n samples, and that corresponds to the distribution p theta tensor to the n, and that is exactly the same as this one, where m2 is also equals m1, and usually omega 1 is the little theta. Okay. So what I have done so far is differential privacy is a requirement on a Markov kernel. So I've given you some examples of Markov kernels. I have told you this how does it act on functions and probability measures. And I've given more than one Markov kernel, there are some ways to construct newer ones. Okay. Now, as you've seen already, there was a notion of a convergence of Markov kernels, or not literally, but we saw a convergence of trade-off functions, those one-dimensional functions. So the talk will essentially be about convergence of class of Markov kernels. Okay. Or yeah. Okay. So I have already said this, that differential privacy is a requirement on a Markov kernel, but what kind of requirement? On a high level, it's a Lipschitz requirement. And yeah. So on a different way said, differential privacy is also a statistical requirement on a Markov kernel. And this is basically what we mean by the overarching framework information. Now, the moment you have a statistical requirement on a high level, the idea is the following, which is where you assume that the adversary who is going to look at the 1 over n summation xi or number of 3 cycles, be it the deterministic outputs or the randomized output, does not matter as of now. But the adversary, how much power does he have? So that's really the idea. So differential privacy assumes that the adversary has the supreme power. That basically means, and I'll explain, statistical power. Now, if you want to weaken it, that you assume that even if your adversary sees the real number 2.5978 or something like that, the adversary is somehow weak in the following sense. Maybe the adversary can only learn the first k digits of your real number output. So maybe the adversary might be weak in some way. Okay. So that's on a high level. This is, as of today, it's just a comment from my side. It's a specific computational requirement on a Markov kernel. Now let's start to formalize what do we mean by differential privacy. So what is differential privacy? So here it is. On a high level, it's a requirement on a Markov kernel. So step back. When we need to define a Markov kernel, what are the things that we need? So Markov kernel, forget about the sigma algebras for now. They are very important, but for now, forget about it. They just need a domain and a range. Okay. And what do you think of omega 1 as in your example? And I'll give those examples right away. So this is the example. So I'll explain this line afterwards, but let's focus on this example. So this is the example when I was telling that you are, let's say, a hospital and you have n persons data or k persons data. Okay. And the other example that I had in mind is the graph. So your Facebook and you have a graph, the Facebook graph. Okay. And okay, so these are two examples to keep in mind. Let's say omega 1. But in order to define a Lipschitz type requirement on M, we need a notion of a neighborliness on omega 1. And on a high level, we need the notion of what we'll call a symmetric relation. So, okay, what is a symmetric relation? It is literally what we learn about relations, which is symmetric relation is if A is related to B, then B is also related to A. Okay. And the high level idea is the following, is that the examples to keep in mind is S, in this case, the hospital case, S is x1 through xn, S prime is x1 through xn, but replace xn by xn prime. And that's actually how we define the relation. In the context of graph, maybe you can think of the Facebook graph, and related Facebook graph will be the following, which is you remove the edge. Okay. So I hope this is clear. So just like even if you forget about all of differential privacy, but if you remember two matrix spaces and trying to define a Lifshitz constant of a function f, then also you need some notion of distance on the left hand side. Here also we need a notion of a distance, but not exactly. It's okay to just have this symmetric relation. And I have given you two examples where how this symmetric relation is usually defined. And in the context of this hospital record, this is the usual where we assume that the Hamming distance is less than or equal to 1. And in the context of graphs, you assume that one graph can be obtained from the another is remove or add an edge. Okay. So omega 1 earlier had a no structure. It was literally a set. Now I have put in a structure which is that of a symmetric relation. Now, so this is how the definition will appear. So I'll keep the standard example in mind, and that is the hospital example. Now this is really the key thing to keep in mind. So this is the definition of differential privacy, or the hypothesizing version, which I'll come soon. What does it say? It says the following: whenever two data points S and S prime are close, that means x1 through xn, but replaced by xn prime, the randomized output M of S and M of S prime, these are, remember, the distributions. So these distributions should be statistically indistinguishable. Okay. So x1 through xn, replace xn by xn prime, and you're releasing something. Somebody is asking you to release 1 over n summation xi, the average height. You cannot literally do that. Why? Because these two are distributions. We are treating them as distributions. That means even if x1 through xn are some random things, I mean, they're coming from a random variable, they are random variables, you have to condition on them and then treat these as deterministic things. So this is what I mean by that. You have to apply external randomness. Okay. Even after having the data set x1 through xn. Okay. So these two distributions, we demand it to be statistically indistinguishable. That means if an adversary sees these outputs, M of S or M of S prime, the adversary does not know whether it is coming from S or from S prime. It sees a real number. It does not know whether it is coming from the data set S or the data set S prime. Okay. So this is, let's say, the hypothesizing problem from slide 1, P0, and this is P1. Okay. So this is what we want. Now, the moment you assume that your adversary is infinitely strong or like statistically strong, and I'll explain what exactly do I mean by that. So this is the information aspect. And the moment you assume that adversary is weak, the one who is seeing the real number but not being able to read all the bits, but maybe the top k bits or n bits of the real number that you output, maybe that adversary is weak. I mean, it is weak. And then, okay, then what happens? So that's the computation part of the title slide. Now we will say that how are you going to do that? So this is where the key thing is, that we're not going to compute the total variation distance between these two distributions and say these are good enough if the total variation between these two distributions is less than or equal to epsilon. This is not what we're going to do. We are going to follow this technique or whatever, the procedure that I described, let's say in the beginning. So we're going to do this via Blackwell ordering. And I'll be brief because I've told this already. So you can think of this PQ as this P, this is Q. These two are distributions. And we'll compute this curve, the curve that we're familiar with, hopefully, by now. So this is the trade-off curve. And okay, so we're going to compute the trade-off curve. Good. And then this is the theorem that I mentioned. This is the set of all taus. So this is the same set as tau, written differently. Do not worry too much. So this 2 is the Gaussian Differential Privacy paper. And the definition says the following. So I'll pause here the longest. So this is the definition of differential privacy. What does it say? It says the following, that, and I am stating the definition for the restricted case, which is the hospital example, but you can exactly define this definition for the graph case as well as the in general set, arbitrary set capital omega 1 with a symmetric relation on it. Okay. So what does the definition says? So the definition says the following, that you consider a base hypothesis testing problem f. So given by f. And how do I construct a function f? I don't have to start with a hypothesis testing problem literally. I will just take an element of tau, the capital tau set. I will take this, so it will look like a curve f. Then I'll define that if I'm able to construct an M that satisfies this condition, I will say that my algorithm, my randomized algorithm, satisfies F differential privacy. So this is the definition. So remember, one of the slides said what is F differential privacy. This is what we mean by what is F differential privacy. So F differential privacy is a requirement on a Markov kernel, and this is exactly the requirement. Okay. And this requirement really captures the intuition that if you assume that F is normal T, the trade-off curve between normal distribution, normal 0, 1 and normal theta 1, then whatever you output as the algorithm designer, you are going to fool the adversary at least this much, F much. And F is like trying to distinguish between normal 0 and normal theta 1. You will say that the way I output my randomized algorithm, the adversary is as confused as the adversary was trying to determine upon looking at a real number, whether it is coming from normal 0, 1 or normal theta 1. Okay, so this is what we mean by relative comparison. That whatever I'm outputting, I'm not comparing with something absolute, epsilon or something, but I'm computing with something relative. Okay. But although that relative also has a parameter, the shifted mean parameter theta, but okay. I guess if you're familiar with the differential privacy, you have obviously seen the definition of differential privacy, the usual one. Maybe for lack of time, I've not stated it, but I'll just say what it is. So the canonical definition of epsilon delta dp is if and only if the same condition as this, when you choose a specific f. So yeah, so a Markov kernel or a mechanism is epsilon delta dp if and only if it satisfies f dp, but for a very specific f. And the key thing in change of perspective from this definition into, let's say this definition came maybe 2003, 4, 5, and this one came in 2020, 21, 22, something like that. The change in perspective is the following, is do not treat through this absolute parameters epsilon and delta, but rather look through the lens of this relative comparison. And where is the power lying behind this, looking through this lens of relative comparison? And this is what I'll explain next. Okay. So this is the object you have all seen. This is so there is only one key mathematical object. This is given two probability measures. I construct this curve TPQ. And this is how it looks like. Usually this is how it looks like. Okay. So I'll skip all of this. So this is the explanation. One thing maybe to mention is this trade-off curve is connected to statistics in the following sense, is that when you minimize this over all measurable functions, you ask the question, this is the this is an optimization problem. So obviously it should have, not obviously it should have, but rather you ask the question, does it have a minimizer? Does the infima is attained? And it turns out in most of the cases, the infima is attained. And what is it attained by? I mean, in all cases, the infima is attained, but in most of the cases, the infima is attained by a likelihood ratio test. Sometimes you have to do randomized likelihood ratio test, but forget about it for now. And what does the likelihood ratio test involve? The likelihood ratio test involves looking at this test, the log likelihood ratio between two distributions. Okay. And this is kind of important. And this is where computation also plays a role on a high level. I don't have anything much concrete to say, but I'll briefly mention that this is kind of important, that although your two distributions P and Q are very separable, that means their trade-off curve is much below the absolute truth, which is 1 minus x. But if you assume that you are not being able to minimize over all measurable functions, and this is literally exactly the same as saying that your adversary cannot solve this problem. Differently said, if you minimize only over polynomial threshold functions, that means indicator of a polynomial greater than or equal to C, and let's say in your problem, the log likelihood ratio between Q and P is not a polynomial, then the question becomes, what is the optimal answer? So that's really the computation part. But we are talking about information, that means we minimize over all measurable functions, not a subclass. Okay. So yeah. And okay, so this is, I'm just explaining the same object, which is the set tau here. And this is the same thing, which is I have a hypothesis testing problem, you have a hypothesis testing problem, we compare each other. And this is also given in the definition. Okay. Now you might say, wait a second, I was happy with the definition, total variation. I compute total variation between P0 and P1. You compute total variation between R0 and R1. And remember, this is the left-hand side of the definition, T of ms, comma ms prime. And this is the right-hand side of the definition, the overarching definition, the F differential privacy definition. Now you might say, wait a second, I don't really care about that definition specifically. Maybe I just want to look at total variation distance between P0, P1, and I will measure it with this. That is a valid choice. But one thing kind of is important, that this definition or this requirement, this condition is equivalent to what is known as the data processing condition. And that basically means that if this happens, then this condition is if and only if, this condition is if and only if, that the hypothesis testing problem that you are trying to solve is a post-processing of my own hypothesis testing problem. Okay. So this is kind of the power that I have a hypothesis testing problem, you have a hypothesis testing problem, and we are trying to understand which one is difficult. Now, what I'm saying is, if I post-process my own data and give it to you, obviously you will be yours will be much more difficult because you have less information. Something like, think about the following, that you have a table of data set and you remove one column and give it to someone else. Obviously, that person will have more difficulty. So removing one column is like applying a Markov kernel, but that's like deterministic one, but okay. Okay, so yeah, so you can skip this too. Now, what is Gaussian differential privacy? So F differential privacy had the definition. Gaussian differential privacy is a subclass, and what does it say? It says the following. So it's the exact same definition, not a single change, except you specialize. So instead of taking an arbitrary F, you take an F, which is that trade-off curve between the canonical example I started with, which is trade-off curve between this normal 0, 1 and normal theta 1. So it's exactly the same definition. Okay, but why is it relevant? And this is where this relevance comes beginning. So the relevance comes from the following, which is instead of one algorithm, instead of one randomized output, I mentioned that somebody might ask you to the hospital, ask the hospital release average height, average weight, and so on. So average height, releasing average height is like applying M1 on your data set from the hospital's perspective. And releasing average weight is like something like this. You can forget the Y for now, capital Y for now. It's like average height, this is average height, this is average weight, and so on. And you can analogously think in the graph case, Facebook has to release number of 3 cycles, number of 4 cycles, and so on. And the requirement that the public are demanding that the first mechanism has to be satisfy this requirement, FDP. It's like a Lipschitz requirement. And 1 over n summation xi does not satisfy that. And this also has to satisfy this. Then the question is of utmost importance, which is when you release both the statistic. Maybe today you release average height, the randomized height. Tomorrow you release average weight, but the randomized average weight. Then you ask the question, okay, now the adversary has 2 information, the output of both M1 and M2. Obviously, then the question becomes, how does privacy degrade? So if M1 satisfies FDP, if M2 satisfies GDP, and the adversary sees both, and this is the ultimate version, the adversary sees both M1 of X and M2 of X. Okay. Then if M1 satisfies this DP and M2 satisfies this DP, then what does the joint mechanism M1 comma M2 satisfies? And this is the result that they proved in their paper, that the joint mechanism satisfies this much DP. And this is where you see in the beginning, I defined an operation on the set tau. I take 2 curves F and G and I define an operation F tensor G. This is that operation. This is what they proved. Okay.
You have five
So
more
this is,
minutes.
oh, sure. Yeah, I'll end. Like I have until 23 slides. So okay. So maybe, okay, I'll try to finish wrap up soon, which is the following. Okay. So what did they prove? So they proved the following. So you can skip all these conditions. These four conditions, does not matter what they are. But what they proved is the following, that if you assume that the first mechanism, you release the information in such a way that it satisfies FDP, but this F subscript n comma 1 dp. The second, when you release, you set the second mechanism M2 satisfies this much dp. And if you keep releasing all this information in a differentially private way, your privacy will degrade. But what will it become? And in the context of high dimensional statistics, you can think of it in the following sense, that you are supposed to release all the neural network weights, and that is like a high dimensional vector. But you can think that you do not want to release the high dimensional vector literally. You want to release it in a differentially private way. Then also you can think that you want to release the first coordinate in a differentially private way, second coordinate in a differentially private way. Now, because this is high dimensional, and if you think the n is the dimension, and okay, so then you can ask that yes. So this is the thought process, that trying to release a lot of information sequentially, or in this sense, how does privacy degrade? And they proved that the privacy degrades like this Gaussian. Okay. Now here, what they saw is the following, which is that the privacy degrades like this, not a problem. But the central limit theorem that they always saw that S square is equal to 2k. Somehow the mean that they are getting, this mean depends on this function. And you can see this is the mean and this is the variance. So this is part of the assumption, just like you assume first moment, second moment finite, and they also assume third moment finite for variation purposes, but I have not stated the variation. But whatever, I mean, for the now, let's focus on this, which is the mean is related to the variance in a central limit theorem. And the question for me was, why is that the case? Is it always the case? And this is what they asked, that in all examples, this is what they show. And they ask a proof of this interesting observation is left for future work. Okay, so this was literally my motivation. And then I will skip this. Okay, so rewritten, what they showed is that if you release a lot of statistics in a differentially private way, and these baselines are F1, F2, F3, and so on, releasing all of them, your privacy will degrade like this tensor product. Now they proved that this tensor product will become this one. This mean is always connected to B, this. The first thing I showed, I observed in my case, which is if I take not this generic FIs, which satisfies those four conditions in their theorem, but this very specialized example where I'm trying to release maybe differentially private community outputs, like community labels are 0 and 1, and I'm trying to release community labels in a differentially private. Maybe I would like to compare with two Bernoullis. This is the baseline if I consider. Then I observe, and this kind of immediate almost, that if you take tensor products of these baselines, you will converge to a Poisson and not a Gaussian. So that led me to the question that if you compose these trade-off functions, or compose or take tensor products, which basically means releasing infinitely many statistics. For example, in a graph community detection type problems, you're trying to release all the community labels in a differentially private way. Or a high dimensional statistic, you're trying to release a neural network outputs in a differentially private way. How will your privacy degrade? They showed generically this will look like this, but this is the example where I showed that it does not look like this all the time. So the question is, what are all the things that look like? And then it leads us to the question that I assume that I have this triangular array and I believe that it converges under this tensor product or composition. Then what will the limiting object be? They showed that the limiting object will always be Gaussian. I showed that not always. They assume this for sufficient condition and they show yes, it is Gaussian. But I saw that it's not always Gaussian. So what always will it be? So this is what I showed. And then I will end with this slide, which is where I show, which is the following, that the Gaussian DP curve that they showed is also belongs to this class, the specialized class, which is this class. The Gaussian also belongs to this class, and the G theta example, if you remember. And then the question is, how do I really prove this? And it turns out that it can be proved by taking an appropriate P and an appropriate Q. Okay. And then it also can be shown that the Poisson example is also part of my class, which is what comes, let's say, when you release Poisson statistics. And then I'll end with the S square equal to 2k. So what they showed is the following, that if you remember, the limiting objects will look like P infinity, Q infinity. And if they had P infinity like this, that means it has only the Gaussian part, not any Poisson part. Then the question is, why will it be the case that S square equal to 2k? The answer is, the first question is it always the case? What I show is yes. And the question is then why? And remember, P infinity is a infinity divisible distribution according to the theorem stated, but it has to satisfy another restriction, which is exponential moment of P infinity has to be equal to 1. And the moment you see that exponential moment of P infinity has to be equal to 1, sorry, this is not P, this is like P infinity. Then we all know that exponential moment of a Gaussian is 1, is the same as this condition. And yeah, so under notion of this convergence or this composition, you'll always have S square equal to 2. So maybe I'll stop here. I have another thing, but maybe I'll pause. Yeah, I'll stop. Yeah. Thank you.
Thanks.
Yeah.
Any questions from